Hello everyone. Today we're gonna learn about Bellman-Ford algorithm. This is a mathematically proven algorithm to find the longest path and shortest path from one node to all other nodes in a graph. Bellman-Ford is very simple, but it plays a very important part on the process of thinking and designing an algorithm to solve an information problem. This tutorial is a part of the Data Structures and Algorithms class. First, we're gonna talk about typical problems solved by Bellman-Ford algorithm. Bellman-Ford algorithm is designed to solve single sorted path or longest path. It can solve both sorted path problem and longest path problem. With Bellman-Ford, it's gonna find sorted path, longest path from one source node to all other nodes in the graph. It's very simple and mathematically proven. If you are interested in a math proof, you can click this link here to read more about it. Here in our tutorial, we only focus on the application. So the problem is we are given a graph and we are asked to find a sorted path from the starting node, which is node 0 here, to all of the nodes in the graph. So what is the sorted path from node 0 to node 1? Sorted path from node 0 to node 3? What is the sorted path from node 0 to node 2? And lastly, what is the sorted path from node 0 to node 4? That's the problem that Bellman-Ford is gonna solve. And Bellman-Ford will also work with negative edges. For example, in this graph, we have the edge from 3 to 2 is negative 10. The condition to use Bellman-Ford for sorted path, which is our case here, is that the graph has to have no negative cycle. For sorted path, the graph has to have no negative cycle in order for Bellman-Ford to work. So in our graph here, we're not considering this edge with the weight of 6. We're gonna talk about it later. And without considering this edge, our graph has no negative cycle. So our graph here satisfies the condition that we need. How to use Bellman-Ford? We need to get all the edges and then relax them v minus 1 time, with v is the number of vertices. So in our graph, we have 5 vertices. They are 0, 1, 2, 3, and 4. And we're gonna get all the edges and relax them 4 times. V minus 1 times, and V is 5. Then what is the relaxation for sorted path? It's the general rule we have here. What this line saying is, if the distance to node U plus the cost from node U to V is smaller than the distance to node V, then the distance to node V gonna be equal to the distance to node U plus the cost from U to V. To translate it into our graph, let's say that U is node 1 here and V is node 4 here. Basically what it said is, if the distance from node 0 to node 1 plus the distance from node 1 to node 4 is smaller than the distance from node 0 to node 4, then we're gonna update the distance from node 0 to node 4 with the value of the distance from node 0 to node 1 plus the cost of node 1 to node 4. The cost of node 1 to node 4 is simply the combined edges from node 1 to node 4. In this case, we only have one edge. But in general case, we might have node and edges in between of 1 and 4. And it's that simple. We're gonna keep doing this for v minus 1 times, which is 4 times in our case here. And then we're gonna have the sorted path from our source node 0 to all the nodes in the graph. So let's run this by hand and see how it works. We have 5 vertices, 5 edges, so we're gonna list them out here. And the way we list them out is, the first number is gonna be the from node, and the second number is the to node. So what we have here is edge 0, 1, which is from node 0 to node 1. And then we have edge 0, 3, which is from node 0 to node 3. We have edge 1, 4, which is from node 1 to node 4. We have edge 2, 1, which is from node 2 to node 1. And we have edge 3, 2, which is from node 3 to node 2. That's all our 5 edges. We also have 5 vertices, 0, 1, 2, 3, 4. So we're gonna relax these 5 edges 4 times. Now before relaxing them, we're gonna initialize the distance from node 0 to all the nodes. For node 0 to itself, the distance is 0. For all other nodes, we first assume that it's gonna be infinity. With the initialization done, now we relax them. The distance to 1 now is infinity, which is this part. The distance from 0 to 0 is 0, which is this part. And the cost from 0 to 1 is 4, which is this part. So the sum of distance to 0 and the cost is 0 plus 4, which is smaller than infinity that we're having right here. So we're gonna update this distance by distance to 0 plus the cost from 0 to 1, which is we're gonna update infinity to 0 plus 4. And that's here, now it's gonna be 4. And that's what we have here. We're gonna keep doing the same thing for all the rest of the edges. And then we finish our first round of relaxing. And we have 4, 5, 11, 4, and minus 5. These are the new values of the distance from 0 to all the nodes. For round 2, we're gonna keep relaxing with the same procedure. And as you can see, by round 3, we already have our result. We relax the 4th time, but it doesn't change. For some time, we don't have to relax for all the time required. For example, in our case here, we only have to relax 3 times. And our final result is the sorted path from node 0 to itself is 0. To node 1 is minus 2. To node 2 is minus 5. To node 3 is 5. And to node 4 is also 5. Let's have a fast check. If we want to go from node 0 to node 4 here, we can see with our eyes that we have 2 possible ways. The first one is this one, from 0 to 1 to 4. And that's gonna cost 4 plus 7, it's gonna be 11. And the second way we go is from 0 to 3 to 2 to 1 and to 4. That's gonna be 5 plus minus 10 plus 3 and plus 7. And the total path is 5, which is better than 11. So the sorted path from 0 to 4 is 5, which is what we have here. So our result here is correct. Now for a soft proof of how it works is that each of relaxation is simply trying different ways to get from the source node to the destination node. For a graph with 5 vertices, if the graph is strongly connected, we have maximum 4 different ways from a vertex to the other. That's why the relaxation is 5 minus 1, which is 4 times here. Next, we're gonna have a look at our implementation for sorted path with Bellman-Ford. This implementation is really simple. Remember, any implementation of mathematically proven algorithm is just simply a procedure, and we translate that procedure into code. First, we have the adjacency list of the graph, which is the code presentation of this graph we have right here. Remember, we don't have the edge of 6 here. We're gonna use that edge for something later. Next is our sorted path Bellman-Ford implementation. Step 1, we have to transform our graph from adjacency list to vertices and edges list. This is another way to present a graph. So we're gonna have a list of vertices and we're gonna have a list of edges. And this simple code here is simply take in our graph and transform it into vertices and edges list. So if we run it, this is how the vertices list is gonna look like. We have the list from 0 to 4 node, and we have the list of edges. The first number is from node, the second number is to node, and the third number is the edge weight. And we have 5 of them here. For step 2, we initialize the distance from node 0 to all the nodes, which is 0 and infinity here. And if we print it out, this is how our initialization look like. From node 0 to 0 is 0. From node 0 to all other nodes, it's gonna be infinity. For step 3, we simply relax the edges, v minus 1 time, which is 4 times in our case. We're gonna do it 4 times, and for each time, we're gonna go through all the edges and apply our relaxation rule here. And we can print the values out to see how it's look like. And that's actually what we see here. So these values here are the value for the first relaxation, and we continue for the next relaxation for the second round, and so on until we finish 4 times. After that, we simply return our result, which is what we have right here. Bellman-Ford is really simple, and this is procedural. That means you can use this algorithm and plug in any input at this type, and you're gonna have the sorted path result. Next, I want to talk briefly about the case where Bellman-Ford doesn't work, which is for sorted path. The graph contains negative weight cycle. So now let's have a look at this graph and include the edge in light shade here from 1 to 3 with the weight of 6. If we include this edge in our graph, it's gonna create a cycle from 0 to 3 to 2. This cycle includes 3 nodes, 1, 3, and 2. And the value of this cycle is 6 plus minus 10 plus 3 is gonna be minus 1. So the cycle value is negative 1. And that's what we have here when we include this edge from node 0 to node 3 with the edge weight of 6. So if we run our algorithm with this graph like this result is not correct anymore. Why? Because the negative weight cycle of the graph, this result is gonna keep changing. If we relax one more time, the graph with no negative weight cycle doesn't change, but the one with negative weight cycle changes. If we relax one more time, and one more time, and one more time, we can see that with the negative weight cycle graph, Bellman-Ford doesn't guarantee the result. For a graph that doesn't have negative weight cycle, Bellman-Ford always guarantee the sorted path. Next, we're gonna see how Bellman-Ford can be used to calculate the longest path. With two very simple modifications from sorted path algorithm, we are able to make Bellman-Ford calculate the longest path. So for longest path with Bellman-Ford, there's only two things we need to change from sorted path algorithm. The first one is changing infinity to minus infinity, which is the assumed distance between the source node to all of other nodes. The second thing is to flip the comparison sign of the relaxation rule. Basically what this says is, we always choose for the bigger number, the longer path. And if we do that, this is our final result. From 0 to 0 is 0, from 0 to 1 is 4, 0 to 2 is minus 5, from node 0 to node 3 is 5, and from node 0 to 4, the longest path is gonna be 11. Now let's have a look at node 4 on the graph. And we're ignoring this edge of 1 for now. So from the source node 0 to 4, with our human eyes, we can see that we have two paths. The first one is 0 to 1 to 4, and that's gonna cost 11. 4 plus 7 is 11. And our second path from 0 to 4 is from 0 to 3 to 2 to 1 and to 4. And that's gonna cost 5 plus minus 10 plus 3 plus 7. So that's gonna cost 5. And between 5 and 11, this path is the longer path. And that's what our algorithm returns. That's the longest path from 0 to 4 is 11. Now let's have a look at our implementation. For longest path with Bellman-Ford, like we said earlier, in this whole implementation, we only have two changes. The first one is here, changing infinity to minus infinity, which is this change that we have here. The second one is choosing the bigger path from the relaxation rule, which is this change from here. We're just changing from min to max. And that's it. So if we run our algorithm, this is the result that we're gonna get. And our longest path from node 0 to node 4 is 11. Now, just like sorted path, there is a case that longest path, Bellman-Ford would not work, which is where we have a positive weight cycle. So if we include this edge from 4 to 2 with a weight of 1 here into our graph, which is this addition here in our graph now have a positive weight cycle, which is this cycle, 1, 4, 2. And Bellman-Ford no longer can return the longest path. So if we run our algorithm with the graph having this new edge, when we have a positive weight cycle, the longest path results no longer correct. And we can check it by doing more relaxation. So you can see longest path with no cycle. No matter how many times we relax, the result doesn't change. But for graph would have positive cycle, if I relax one more time, and another time, and another time, we can see that the result keep changing. So Bellman-Ford longest path doesn't work with graph that has positive weight cycle. Next, let's talk about the importance of finding the longest and sorted paths. If you have noticed, Bellman-Ford is the first algorithm that we learn to find the longest path and sorted path. It works by listing all possible sorted paths and longest paths, and actually that's more like a brute way. Instead of array, this is gonna be on graph. Bellman-Ford is also math proven, so the algorithm guarantees the correct result. This is very desirable in software engineering or information problems that we want to do maximization and minimization. So if we think about it, if we can present any problem in form of a graph, then it is guaranteed to find maximum or minimum. Then the maximization and minimization problem is solved. So it's very easy to use and it's rarely asked in coding interview. But this role of Bellman-Ford for maximization and minimization is very important in our thinking process on solving problem. Because again, if we can present our problem in the form of graph, then it is guaranteed to find the minimization or maximization of our problem. And in fact, in our problem, we can almost always present a problem in the form of graph. So the key takeaway is, if you see a maximization and minimization problem, if you can present your problem in graph, then it's guaranteed that you can solve your problem. Next, let's summarize our Bellman-Ford algorithm. First, if we want to find a truth about our data, and our truth is finding the sorted or longest path, and the input is graph, or we can present our problem with graph, then we can use Bellman-Ford to solve our problem with a time complexity of OE times V, where E is the number of total edges, and V is the number of total vertices. Now, Bellman-Ford also solve our maximization or minimization problem, which is very desirable in solving information problems, like maximizing the profit and minimizing the cost. If we run into this kind of problem, we now have Bellman-Ford, as long as we can fit in a graph or present the problem with the graph. Bellman-Ford guarantee a solution. Now, sometimes maximization and minimization is also an optimal problem. So if we want to find a most optimal solution, like sorted or longest, or min or max, we can think about Bellman-Ford. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.